Okay, so in this case study in non-equilibrium, we're going to be taking a look at what happens whenever we have rolling with slipping. Now, remember that our no-slip conditions are going to be, or just one of them really is all we need. VCM is equal to omega r. And the others are going to be used in conjunction with the rest of the problem, basically. So what we have is a bowling ball which has been released without rotating and just kind of thrown down the bowling alley. And you all have experienced this. You've seen it if you've ever gone bowling, that somebody will throw the ball and either it won't be spinning, which means it must be slipping, and then eventually it starts to roll, and at some point it's going to be rolling without slipping. But it takes some time for that to happen. And so what we're looking at now is just exactly how do we go about this particular kind of analysis. And so for our purposes, all we're going to say right now is that it's released with some V initial, it's not rotating, and that there's going to be a coefficient of mu sub k. It's going to be a kinetic friction because it is sliding. And so these are going to be the only two conditions that we have to start with, at least. And so basically what we're looking for here are two things. A, we want to know how much time it's going to take for it to stop slipping, and B, how far does it go before it stops slipping. So those are the two quantities that we're interested in. All right, so what we have is VCM, and I'm going to go down through the middle and you'll see why in a minute. VCM is equal to omega times r. So I'm just basically going to call this home base. And the first thing we're going to do is work on VCM a little bit. All right, now when it comes to VCM, it's going to be governed, kinematically speaking, by VCM is equal to V initial plus AT. Now, the only problem we have here is we don't know what the acceleration is. And so in order to get the acceleration, we're going to have to use Newton's second law. So with Newton's second law, we have F net is equal to ma, and a is therefore equal to F net over m. So before we go any further, now that we can see that we have force involvement, let's go ahead and draw the forces on our diagram. Okay, so what forces do we have acting? Well, we have the normal force as a contact force. It's going to point straight up. And then we have the friction force, which is going to be pointing straight to the left, and it's parallel to the surface. And then finally, we have the force due to gravity, which is acting from the center of mass pointing straight down. So that is our FBD. Okay, so what do we put in for F net? Well, we're looking at an acceleration which is in the x dimension, and there's only one force acting in the x dimension, and that's going to be the force due to friction. So the acceleration is equal to the force of friction divided by m, and this is going to be negative because it points to the left. So the acceleration is equal to minus mu times the normal force, which is mg, divided by the mass. So mass is going to cancel, leaving us with an acceleration, which is just equal to minus mu g. Okay, so we can add that to VCM. We get VCM is equal to, now V initial minus, we have V initial minus mu g times t. And so we're going to substitute that in for VCM. So we get V initial minus mu g times t is equal to omega times r. But now we've got to transform omega into something which is more meaningful. And the way we're going to do that is we're going to use omega final is equal to omega initial plus alpha t. Now, you might be asking yourself why you're doing that. Well, the reason we're doing this is because omega changes as a function of time, just like VCM is changing as a function of time. Remember that we're going from, when it comes to omega, 0 rotation to some rotation which fits the no-slip condition. And then when it comes to VCM, we start off with a large initial velocity, which then decreases over time to some lesser velocity. And so that's what we're doing here right now. We're figuring out what is omega as a function of time. So we know that omega initial is 0. So that gives us omega final is equal to alpha t. Now we have to get alpha, and alpha is just angular acceleration. So once again, we're going to have to go to Newton's second law. And Newton's second law for rotation is tau net is equal to I alpha. Now, in this case, we're going to use the center of mass as the axis of rotation. That's far and away going to be the easiest way to look at this problem. And so that's what we're going to do. Now, if the center of mass is going to be way up here, then we can ignore the torque due to gravity. We can also ignore the torque due to the normal force, because R for the normal force is down, and then the normal force itself points up, and that's going to give us 180 degrees for phi, and the sine of 180 is 0. So all we have to worry about is the torque, which is going to be due to friction. And because this torque is causing a clockwise rotation, it's going to be negative. So we get minus R perpendicular to F is equal to I, which is 2/5 mr squared, times alpha. And so we know that the force due to friction is going to be mu mg. So we get minus R, capital R, because that is R perpendicular, times mu mg is equal to 2/5 mr squared alpha. And so let's go ahead and cancel out this R with that R, this M with that M. And remember, we're solving for alpha. So that means alpha is going to be equal to 5/2 mu g over R. So now let's substitute that back into our omega as a function of time, and we get omega final is equal to 5/2 mu g over R. Okay, so let's go ahead and substitute all of this back into our base equation once again. So we have V initial minus mu gt is equal to omega. Now omega is equal to 5/2 mu g over R, and let's not forget the t right there. So let's make sure that's in there. And so we get omega is equal to 5/2 mu g over R times t. And that's omega. So this is what we substituted for omega, and then we have an R out here. So we can go ahead and cancel this R with this R, and we'll move some terms around. So we're going to get V initial, just doing some algebra, is equal to mu gt plus 5/2 mu gt. So V initial is equal to 2/2 plus 5/2 is equal to 7/2 mu gt. So we're going to get Just rearrange it now for t, and we get 2/7 v initial over mu g is equal to t. And that is the answer to the first part of our problem. Okay. Now, what is the displacement? That's what we're looking for. How far does it travel by the time it stops slipping and just rolls? Okay, so in that case, for part B, we're just going to use, well, it doesn't matter which one of our kinematics equations we use, but let's just stick with an easy one. So we get d is equal to v initial t plus 1/2 at squared. And we know that the acceleration is equal to minus mu g, so we can put that in here. And we know that t is going to be equal to all of that stuff there. So at this point, I would recommend just getting a number for it. And so just find a number for time, and you substitute that in here and here. And v initial is going to be given in the problem. And so we have everything we need. It becomes a straightforward plug and chug kind of problem.